Hello everyone, welcome to my YouTube channel. This is my second video on longest common subsequence. In the previous video, I covered how to solve it utilizing recursion. And then the recursive solution will lead to time limit exceed error. But this is a good starting point, especially during the coding interview, to illustrate your idea on how to solve it. And then you can do some optimization on top of that. The second solution is the recursion with memorization. It's also called top-down approach. So in that approach, we utilize a cache dictionary to store the value we have already calculated in the recursive approach. So in that case, it avoids repeatedly calculating the same value over and over again. We also covered how we went from the solution 1, the pure recursive approach, to the solution 2, the recursion with memorization. The idea is, let's say, when we're trying to look at the first solution, the recursive solution. When we check it, we try to walk through the execution with the example 3. And then we are trying to write out, okay, the first it execute LCS 00, and then in order to execute this one, because in this example, A and D, they are not equal. So it's equivalent to calculate the maximum of LCS 01, LCS 10. And then we calculate these two functions respectively. And then these two functions, we write out how to calculate them, and then we realize there is some overlap. So this LCS 11 is calculated repeatedly. So in that case, how to reduce the runtime? We are trying to avoid the repeated calculation by utilizing a cache. So which is a Python dictionary, or you can also call it hash map in other programming languages. We utilize that to store the value we have already calculated. If the value is already calculated, we just fetch that value from the cache. If not, then we just calculate it and then put the calculated value into the cache so that next time when we encounter the same value, we can just fetch them. So that's kind of the optimization. So, and then with this recursion plus memorization, this top-down approach, we kind of pass all the test cases, and then there is no more time limit exceed error. In the third approach, is more like bottom-up. So in the recursive approach, what we are trying to do is we are utilizing a cache, a hash map. So it's more like a top-down approach. But in this dynamic programming, we utilize the bottom-up approach. So similar idea, instead of utilizing the cache, we create a matrix called DP. What does DP mean? So DPIJ, it means, okay, the length of the longest common subsequence in substrings. In those two substrings, one substring starting at index 0, ending at index I minus 1. So it's a substring of length I. And then another substring is the substring starting at index 0, ending at index j minus 1 in the text 2. So the substring of length j in text 2. So that's kind of the meaning for DP. So I know in my previous video, I kind of incorrectly mentioned the ending in index I and index j. So now in this video, I'm correcting that. So I think this explanation makes more sense. So, okay, in this case, what are we trying to do? So starting from the base case, the base case is we start with the substrings with length 1, which means I equals 0, I equals 1, and j equals 1. That's the substring starting at index 0, ending at index 0 as well. So comparing the first character. That's why when we're trying to loop through it, our I start from index 1, j start with index 1. And then we are doing the comparison. Comparison is, let's say, if those two characters, if they're the same, then we increase the value of the length. So basically, we extend the length by 1. That's why it's 1 plus. If they're not equal, we consider two cases. So it's either the I minus 1 j or I j minus 1. We pick the maximum from the two. And then in the end, what we want to calculate? We want to dpmn because we want to get the longest common subsequence in the substrings starting at 0, 0, at index 0, ending at index m minus 1, and then n minus 1, which means or tax 1 and tax 2. So that's kind of the review of the solutions we covered in the previous video. So now I want to talk about how to optimize the space. So in the solution 3, because we are creating a matrix of dimensions m plus 1 times n plus 1, so the overall space complexity is OMN. We are trying to optimize the space for this dynamic programming approach. So let's take a look at the DP matrix we created. So basically, in each iteration, what are we updating? So there are two different scenarios. One scenario, dpij equals 1 plus dpi minus 1, j minus 1. In the other scenario, dpij equals the maximum of dpi minus 1 j, dpi j minus 1. Have you find a pattern? So basically, in order to calculate dpij, we just need to know the previous column and the previous row at maximum. So in that case, we are trying to optimize the space, trying to reduce this one. So we are not utilizing a matrix of dimension m plus 1 times n plus 1. Instead, we are trying to think about how we can keep track of the previous row or the previous column. So in that case, let me try to modify on top of the previous solution. So instead of utilizing dp to store that, I'm trying to utilize just two variables. One is called previous, and then the other one is called current. So previous indicates, okay, previous row, and then current, in this case, the current row we are calculating. Since each row contains all the elements, each row contains the element of all the column in that row. So in that case, we automatically covers the previous column. So in that case, let me try to set up the initialize the previous one. So at the very beginning, the previous one should be the Now I'm trying to do the modification. So in that case, let me see. Okay, we replace dpi with current, and we replace dpi minus 1 with previous. So current row and previous row. And then dpi equals current row, and then dpi minus 1 equals previous row, dpi equals current row. Okay. So And then in that case, so after we do the assign, let's say the previous equals the current. Okay, so by submitting this solution, you can see that, okay, the memory usage is less than 91.92%. So this one is the solution with optimized space. So let me try to go over how we derive this solution. So basically from the previous solution, solution 3, dynamic programming bottom-up approach, we utilize the matrix DP of the dimension m plus 1 times m plus 1. So in that case, the space complexity is OMN. And by looking at how we do the calculation, we realize that, okay, at each iteration, what are we trying to access is actually the current row. So I indicates the current row. And then I minus 1 is the previous row. And then j minus 1 is the previous column. So basically, you are just trying to access current row, previous row, current column, and previous column. So that's all. So in that case, we do not need to keep track of the entire matrix all the time. What we need to keep track of, that's kind of the modification. So we remove the matrix DP. Instead, and then we replace with two rows. So previous means previous row, current means current row. So in that case, we have access to the current row, previous row, current column, and previous column, since each row contains all the columns as well. So before start of the iteration, we first initialize the previous one. So at the very beginning, it's just 0. We do not have any longest common subsequence available. And then when we're trying to iterate through each row for I in the range of 1 to m plus 1, we just assign the previous row value to the current row before we start updating the value for the current row. And then after we assign the previous value to the current row, the value of previous row to the current row, we're trying to iterate through each column, and then we are trying to do the update. So compare these two solutions. So one point is, so previously, if we ever encounter DPI, we replace it with current. That's current row. If we encounter DPI minus 1, that is previous row. So in that case, we replace DPI minus 1 with previous row. The column index remain the same as the previous solution. That's kind of how we consider the two different scenarios. And then in the end, after we finish the calculation for the current row, in this case, we try to assign, we need to update the previous row before the start of the next iteration. Because remember, when we move to the next value of I, the current row becomes the previous row. So that's why in here, we assign the value of the current row to the previous row. So that's kind of the entire idea of doing the space optimization. So in this case, the time complexity is still OMN, but the space complexity is reduced from OMN to ON. Or more precisely, I think we can try to do, here we just pick N and then create a array of dimension N plus 1. If you really want to further optimize, you can actually try to check out of M and N, which one is the smallest one, and then pick the smallest one. And then in that case, your space complexity will become the minimum of M and N. So that's kind of the solution with optimized space.